Okay, let's dive into this. We've all seen those pictures of the sun, right? With those dark patches on it. We call them sunspots. But there's so much more than just blemishes. They are the surface signs of a massive magnetic engine. And for decades, they've been at the center of a puzzle that seemed to break the basic laws of physics.
So what you're actually looking at here are called bipolar magnetic regions, or BMRs for short. The easiest way to think about them is like you're seeing the north and south poles of gigantic magnets that are literally poking through the sun's surface. These are our clues to what's happening with the incredible magnetic fields churning deep inside our star.
And you'd think, right, that just like magnets here on Earth, these solar magnets would have to follow certain rules. Fundamental laws of physics that say how they're supposed to behave. But for the longest time, it really looked like the sun just wasn't playing by its own rulebook.
And this brings us right to the heart of our mystery. It's kind of like a detective story, but one that's written in magnetism and light. Let's call it the tilted puzzle. So the main rule we're talking about here is called Joy's law. It's a really big deal in solar physics. What it says is that these magnetic pairs, they shouldn't be lined up perfectly east-west. They should actually be tilted. And this is the key part. The farther a sunspot pair is from the sun's equator, the more tilted it should be. It's supposed to be this really neat, predictable pattern.
But here's the thing. When scientists actually went and plotted the data from thousands and thousands of real sunspots, the pattern wasn't neat at all. It looked like this, just a messy, noisy cloud of dots. Joy's law was so faint you could barely see it. It was like trying to hear a beautiful song in a room full of static. So what was going on? Was a fundamental law of physics just wrong?
Well, a team of researchers had a hunch. They thought, maybe the law isn't broken. Maybe we're just not looking at the evidence correctly. They realized that to crack this case, they had to be there right at the very beginning. They had to catch a sunspot being born.
You see, the problem was that most of our automated tools for finding sunspots, well, they're like detectives showing up way too late to the crime scene. They're built to spot big, strong, obvious sunspots, but by the time they see them, all the important clues from their birth are long gone. Let's see what that actually looks like. 10 hours before a sunspot is officially detected, this is all you see, just some faint magnetic noise on the surface. It's almost impossible to tell that something big is about to happen. Now, fast forward 5 hours. Okay, now you can just start to see it. Those red and blue magnetic poles are starting to pull apart and get stronger. They're emerging from all that background chaos. And this is time zero. This is the moment when the old computer programs would finally go, aha, I found a sunspot. But just look at how much has already happened. All those crucial early moments were completely invisible to us. And finally, we get the end result. A fully grown, mature bipolar magnetic region. This is the sunspot we all recognize. But the real story, its origin story, was totally hidden from science. Until now. To finally see that hidden story, scientists needed a totally new kind of tool. What they really needed was a way to rewind the clock on every single sunspot they found. So they built what's basically a solar time machine. Here's how it works. First, the algorithm finds a mature sunspot and tracks it. But then, and this is the absolute game changer, it uses the sun's rotation to go backwards in time, frame by frame, rewinding everything to pinpoint the exact moment that magnetic field first punched through the surface. And they didn't just do this for a couple of sunspots. Oh no. Out of a catalog of almost 12,000 regions, they managed to successfully rewind the clock on over 3,000 of them. This was a massive forensic investigation of the sun's recent past.
So, once they had all this brand new data, all this rewound evidence, they made a breakthrough discovery. The key to the whole puzzle wasn't just in what they were seeing, but in realizing they were actually looking at two totally different kinds of sunspots.
This right here, this was the aha moment. When they plotted the magnetic strength of a region at its true birth against its strength when the old tools would have spotted it, the data just split. It wasn't one big messy cloud anymore. It was two completely separate groups that were hiding in plain sight the whole time.
So this basically created a lineup of two suspects. On one side, you have the emerging BMRs. These are the real deal. They start small and then show a big increase in something called magnetic flux, which is really just a measure of their total magnetic energy. They grow stronger, just like they're supposed to. But then you have the discarded BMRs, the imposters. These guys don't really grow at all. They're often just the decaying leftovers of old sunspots, pretending to be new ones and totally contaminating the data.
And get this, how many of these imposters were there? A staggering 27%. More than a quarter of the data scientists were using to test a fundamental law of physics was basically junk that was just muddying the waters.
So, what happens when you finally unmask these imposters? What happens when you just pull them out of the dataset and take another look?
Well, the answer becomes incredibly clear when you separate them out. So on the left, that's the original, messy data with everything thrown in together. But now look at the right. When you plot only the imposters, there's nothing there. No pattern, no correlation, just random noise. They were the source of all that static the entire time.
And so, the moment you take them out, the picture becomes crystal clear. Joy's law, that fundamental rule about how sunspots are supposed to be tilted, just pops right out of the noise, with incredible clarity. The law was never broken. Our way of looking at it was.
Now, this is a fantastic piece of scientific detective work, for sure, but it's not just some academic puzzle. So why does solving it actually matter for us, here on Earth?
Well, here are the big takeaways. First, it just goes to show that how you look at data is just as important as the data itself. By cleaning up their dataset, scientists were able to see the true physics of the sun's magnetic engine, and a deeper understanding of that engine helps us understand the whole 11-year solar cycle, which is absolutely crucial if you want to get better at predicting space weather, things like solar flares that can knock out our satellites and even threaten power grids down here.
The scientists who did this work really said it best. They wrote that including these imposter regions can severely mask the intrinsic properties of the real thing. It really leaves you with a fascinating question, doesn't it? How many other secrets of the universe aren't hiding in some new discovery, but are just waiting there for us to find them, simply by cleaning up the data we already have?